Hi, in this video, we are going to take a first look, an introduction into logistic regression. All right, so logistic regression is the #1 statistician way of modeling if an event is going to happen. Now, when we talk about events, we're going to have two possibilities: yes, no, true, false, success, failure, pass, fail, sick, well. Two possible outcomes are what we're going to be focused on. Later in the video series, we'll talk about, more than two possible outcomes. But for right now, we're going to master exactly two levels, and then we're going to proceed from there and use that to expand forward. All right. So one thing we're going to do to standardize things is that when there are two different levels, we're going to have one be a 0 and the other one be a 1 in our notation. Why do we do this? Well, first of all, standardize what's going on so we can be consistent and communicate things. Also, if I have the level of interest is a 1 and I have all 0s and 1s, then taking the average tells me proportionately how often it happened in my data set. So this is a good step, good approach to work things out. Okay, so when I say my model, what we're going to end up doing is that I've got the probability that the event is equal to 1. So this may be the probability that the device is broken, or the probability that the patient is sick, or a probability of the correct answer being true, or the probability of a student passing a class. So however I'm going to work this out, we're going to say that the event that we're interested in for the probability, we're going to denote that as a 1. And then we're going to use this format of an equation to model the likelihood of something happening. All right, so let's take a look at this for a moment. All right, so ignore this for the moment. Just for a second, ignore this. Notice that I have a 1 on the top, the numerator, and the denominator I have a 1, and I have an e to the power of something. Now, if we remember from our college algebra, pre-calculus, calculus, wherever you were exposed to, anytime I have a positive number to an exponent, whatever that exponent is, that has to be greater than 0. Okay, so what that is saying is that this part here, regardless of what these betas and x's are, this part here has to be greater than 0. So I have 1 divided by 1 plus something greater than 0. Okay, so we know that the denominator has to be greater than the numerator. All right, so we know that this has to be less than 1 in magnitude. Okay. So now looking at this also, if this has to be positive and I add the number 1 to it, well, that's a positive number. A positive number divided by a positive number is also a positive number. So we know that this whole thing has to be greater than 0. So we know that our probabilities when we model them are going to be between 0 and 1. That means it makes sense to be working with our probability. So everything is between 0 and 1, strictly speaking. All right, so now let's get into the little bit uglier aspect of the formula. Notice I'm going to have a beta 0, then we're going to have beta 1 times x1. That's coefficient times predictor variable x1. And then I'm going to have a beta 2 times x2, beta 3 times x3, and all the way up to, let's say, beta k times xk. All right, so k is the number of predictors that I have for this. So when I look at this, think of like linear regression. Now, something you'll notice that if you paid close attention to your linear regression course is that linear regression always has an epsilon term for those errors, for the things that are not accounted for in the system. We don't have that. All right, so what we are doing here, this is very different than the regular approach to linear regression, is that we're not trying to actually model the individual value. We're trying to model the expected value. Well, and the expected value equal the probability of the event occurring given the value of the predictor variables. Right, that is something that is important to keep in mind, is that we are modeling not the actual value, not a 0 or 1, but the expected value, that is the probability of 1 occurring. And when I say expected value, think like a Bernoulli random variable. So logistic regression has the probability aspect of this to address the randomness of the observation. So I'm dealing with a probability. And so there's automatically, just with that statement there, I'm accounting for the fact that it fluctuates. It could be a 0, it could be a 1, sometimes it's 0, sometimes it's 1. And we're not going to actually address the individual points. That epsilon term in regular linear regression addresses those individual fluctuations from average. Here in logistic regression, we're not going to do it. We're not going to address it. We're just going to say, on average, that's it. All right, so now, how do we actually estimate the logistic regression model? Well, what we're going to do is I'm going to take my data, and I'm going to use the GLM function to do this for me. So this is the generalized linear model. Now, something that's very important when I do this is that here I've got generalized linear model. I'm going to specify the formula that I want to have. And the format in R is I've got the target variable, the zeros and ones, or some other binary target variable, two different levels. Depends on, see that tilde, and I'm going to have the predictor variables over here, just like I do with regular old linear regression. So here's the formula parameter. Now here I'm going to specify the data. And now here, this is super important when I do this, that I have to specify the family. If I don't, I'm going to get something else entirely. So if I don't do this, R is going to assume I want Gaussian, which is in fact regular old linear regression. So I need to put in the family. I have to put the family in a binomial. Now I have two different ways I can do this. I can either do a quotations binomial, so binomial in quotations, or I can put in the function binomial in there. I prefer to put in the function itself because that'll give us more options down the road. But it's pretty standard. If I do binomial with the quotations, it will use the logit-link function by default. All right, and so then I've got plenty of functions I can work with whenever I use a standard generalized linear model in R. And so here I get the results. We have the deviance of our residuals, and we can see our coefficients. And so we have the intercept term. So that was that beta 0. Then I have class, second class, third class, and crew. What's going on here is that these are dummy variables based off of the baseline level. The baseline level in R by default will be the very first level. If it's a factor, it will go off of the first level. If it's not a factor, it will go alphabetically what's first, which would be first class on this one. All right, so here, this hypothesis test is checking to see, is this level different than first class? Is this level different than first class? Is this level different than first class? Now, it could work out that maybe if I dug in deeper, maybe I should have combined second and third class, or maybe all three of these together. Don't know. I'm not going to dig into it here. Now here, we have male and female in the data set, and this is making a dummy variable automatically, just like R does for linear regression, of female. So if it's a 1, it's a female, 0 if it's male. And then we also have adult or child in this data set, and this is another dummy variable for us. All right, and then we get our null deviance with degrees of freedom, residual deviance, and our AIC. We will be using AIC a lot on this. And now here is the number of iterations that were fitted to get the model. So something about logistic regression is that there is no closed formula for figuring out what the parameters should be. If I'm doing linear regression, there's a straightforward linear regression matrix formula that just spits it out for us straight away. We get an exact value, same value every single time. Unfortunately, with logistic regression, it's an iterative process. And something we need to pay attention to is if it takes a lot of iterations to converge, that's a sign I don't have a good model. It's a bad pairing of model structure with my data. Here, 4, that's no problems at all. If it's like over 1,000, I'm going to start getting concerned. That's never actually happened with linear regression Bayesian models. I've had that problem with, but not in this lane that's for this video. All right, so now the coefficients, when we interpret the coefficients, things are not straightforward. All right, so let's scroll back up to that formula we had before. All right, so in this formula, you notice that my coefficients are, they're not just inside a fraction. They're not just inside exponential. They're in the denominator, and they're inside an exponential, and they have a negative sign on them. So this is pretty complicated. These are pretty well embedded. It's going to work out, we'll show this in a future video, that there's a connection between the log odds and the coefficients. All right, so when I look at the coefficients to interpret them, I'm going to have to interpret log odds instead of the regular value. So if you think about linear regression, regular linear regression, when a predictive variable goes up or down, I use a coefficient to determine on average how much the target variable will change. Not the case here. We can't even say that for probability. So remember, like if things were to grow with a probability, it potentially could go above 1, could go below 0. That wouldn't make sense. Things are trickier here. We have like an S-shaped curve going on. And because of all this, we're going to have a more complicated interpretation. And we'll get into that in another video. Now, we're going to need to evaluate our model, and we'll have a whole bunch of different ways to approach this. There's going to be like classical statistics ways, such as AIC, BIC, like all the techniques that we have for linear regression. Most of them are going to come into play in some way, shape, or form. But we'll also have ways of like new machine learning approaches of like holdout sets. Here, I'm not going to start worrying about holdout sets just yet. I'm taking the point of view that I'm in a classic statistics situation, that I'm going to use all my data to get an inference instead of doing something like a predictive model. All right, so what we're going to do is the number one way that we are going to evaluate our model is that we're going to take a look at its accuracy, and we're going to take a look at features that nuance the accuracy. Like when I say that the Titanic survivor or Titanic passenger survived, how accurate was I? Considering I said survived, or considering I said that they died, how accurate was I? When they really died, regardless of what the model said, how accurate was the model? When they really survived, how accurate was the model? And we'll consider like balance aspects, and we'll really get into it. But the first thing that I want to do is get a confusion matrix. This confusion matrix, what I'm going to do is, did they survive? Yes or no? This is the true thing. Did they survive? Yes or no? This is what the model says. And what I want to have for a perfect model, I want everything on this diagonal here. When the model said no, it actually was a no. When the model said yes, it actually was a yes. Ideally, I want these values to be big. I want as little as possible on these diagonals. Now, the best way that I've found in R to produce this confusion matrix is to use the caret packages confusion matrix function. And from the information, this function immediately spits out a lot of information. So right out the gate, I can see that my accuracy is about 0.75. I'll say 0.75, 3/4 of the time is accurate. Okay, and we'll get a confidence interval on our accuracy. We'll get information rates. There's a whole bunch of things that we can use. Sensitivity, specificity. We'll define all these and dig into these later. Balance accuracy is one that I like to use because this takes into consideration how lopsided is the situation. If we have if survival is very, very, very rare, like 1%. I could get a 99% accuracy by saying everybody died. And so when I have the extreme situations of imbalanced data, just raw accuracy isn't good enough. We want to consider other aspects. Now, some model diagnostics to check is that here, some assumptions that we need. First and foremost, we need to have 2 levels for our target variable. If I have numeric values, if I have 3 levels or something like that, it doesn't make sense to use this modeling structure. Also, another assumption is that I have that log odds relationship with our coefficients. Those coefficients have to be equal to the log odds of the event. We're going to make the assumption when we build the model, we have no multicollinearity among our predictors, just like in regular linear regression. We have no independent, or we have to make sure we have an independence between our observations. And also, here's one that is particular to logistic regression. We have to have no perfect situation, no perfect separation. What I'm saying there, let's say I have a predictor variable that goes from negative 100 to positive 100. And I see that for all values greater than 50, we have positive, and all values less than 50, we have negative, and for the target variable, and it's a perfect separation. All right, when we do this perfect separation thing in real life, if I actually had this, I would just say, look at this one particular variable and just say this is a cutoff between the classifications, and wouldn't even be doing it really a logistic regression at all. The logistic regression modeling process will break down if I actually have too good of a situation. And so this perfect separation is too good of a situation that, really, I don't even need statistical modeling for this. All right, now something that we're going to talk about a lot is checking multicollinearity. This will be a huge problem for us if we have it. And so one of the ways that we'll evaluate this is the variance inflation factor. And the larger the variance inflation factor, the more redundant a variable is considering all other predictor variables. All right, so that's the end of this. So, for your homework, what I want you to do, I want you to build a logistic regression model using your own data. And then I want you just to compute the confusion matrix on your model's predictions. That's it. I submit that in Canvas, web courses, and that's all I got for you. All right, so life is short. Do math.